So, yeah. So we can start again. Now, so now we can form an image of holomorphic maps between compact Riemann surfaces. So there are two types, right? So in general, for any f from x to y, holomorphic, non-constant x compact with degree of f equal to d, two things can happen to for such a function. Either it is unramified. First case, the simplest case, f is unramified. So there's no ramification points, i.e., there exists no ramification points. And in this case, F is a default covering map. Then F is a local, local biholomorphic map. And in fact, is a default covering map. It's a default covering.
Is this in the case where f is unramified?
Let me just write it. Sorry?
Is this the second case?
No. This is the first case. I still in the first case.
Okay.
I said in X. So F is unramified. Then.
But if it's a default covering map, doesn't it make every point a ramified point because every point is d to 1?
Yeah. So the map is really D to 1 at all points.
So
Yes.
every point is a ramified point. No?
No, it's not ramified. So no, that's not possible. You see, the picture that we should have in mind is the following. This is Y. And here, if you look at the inverse image of every point, there are D points in it. So there are D points at all points, basically. There is no crossings coming. But then you see, this picture works only well up to some point, because I cannot draw a picture which is connected at the same time and has that property, because that happens with surfaces. So it's not possible to draw the exact picture of that situation. But this is kind of okay. And so this is a default covering map in the sense of topology, and everything is nice and da da da. The second case, which is much more interesting, and it happens, is that F is a default covering map. So F, is a ramified. F is ramified. Of degree D. So the picture that we should have in mind in that case is much more sophisticated. So this is X, this is Y. Again, there are some points. Most points are nice. So the inverse image is, there are D points in the inverse image for most points. But there are some points, namely the branch points, where inverse image in the branch points is much more interesting. So in this case, there are some. For example, here is five of them, and here there is another branch point here, and maybe this also comes and intersects that. All this intersect each other, this one, and then they go here, and then so there is one here, and there is one here, and so on. So it's much more interesting, and this is called the I don't know, the branching profile of the function. In a way, now topologically, we understand these holomorphic maps within compact Riemann surfaces. They are either ramified covering maps or unramified covering maps. Okay. So that picture is not very good, but we had pictures before. So. Okay, now let me just do one more. Okay, so let me write now Riemann-Hurwitz formula in a different form in terms of genus rather than Euler characteristic. So now, remember Riemann-Hurwitz was like this, chi x is equal to b times chi y minus some multiplicities at x of f minus 1 over x. Oh, yeah, okay, so f from x to y is a default covering. Oh, no, I mean, this is degree D, sorry. Okay, so if you write these things in terms of genus, I'm going to write it like this. So what notation I use? Did I use G? I just use G now for the yeah, for the domain, yes. So write chi x equal to 2 minus 2g and chi y equal to 2 minus 2g prime. So or you can just use gx and gy, right? So then star is equivalent to this formula now. G is equal to b over 2 plus d times g prime minus 1 plus 1. But b is the sum is this quantity, sum multiplicities at x of f minus 1 and okay, so x belonging to x. And this quantity is always non-negative, by the way, because multiplicity is either 1 or bigger than 1 around that point. Okay, so if you look at it, then you get first a beautiful conclusion, namely, you cannot have a holomorphic map into a Riemann surface that has a higher genus. So G prime, so the first corollary is the following. I mean, if you look at it, is that G prime is, I mean, look, I mean, G, this is, but B is non-negative, right, here. B is non-negative. This quantity is either -1 or 0 and positive, could be. So you can argue what happens if this is 0, because then, of course, so let me. But this one, so G prime is okay. So what kind of? So this is the Euler characteristic for that. So G is always bigger than or equal to G. Yes, that's what I. No. But what I'm trying to say, yes, I think that's correct. Yeah. Do you see this? Are you okay with this conclusion? You see, look at cases. If G prime is 0, and you see here is we have to be careful. G is the Euler, is the genus of X. G prime is the genus of Y, right? G prime is genus of Y. Okay, if G prime is 0, then of course G is also bigger than or equal to 0. There's no problem to worry about that. So that's okay. So then the next case is G prime is 1 or bigger than 1. In this case, this quantity is positive and it's multiplied by some D, which is 1, 2, or so on. So then it follows that G is actually bigger than G prime in that case, because there's some multiple of G prime plus something. So this is bigger than that.
But there's a minus D, right?
This what?
There's a minus D.
Not minus D. No, no, no. G is D times G prime minus 1. And then there is this quantity added. So this is always good. Oh, you're worrying about this?
Yeah.
Yeah. Minus D. Yes. So what I say is that G prime bigger than G is impossible. So maybe I write it. Huh?
If you plug in G prime equals.
So let me write it G prime bigger than G. I just write it like this, is impossible. Oh, so that's exactly i.e. G is G should be bigger than or equal to G prime. Yeah.
I think the problem is solved because when we plug in G prime equals 0, we know that G prime is greater than or equal to 0. So B over 2 plus 1 is greater than or equal to minus D.
Okay.
Is greater than or equal to D. So by that logic, that minus 1 is not going to cause any problem.
Yeah, that's right. So yeah, I agree. I mean, this happens. I mean, this is correct. Yeah. The second case that we can. Now, if the genus is 1, now imagine G is equal to G prime is equal to 1, i.e. F is a map that goes from a surface of genus 1 to a surface of genus 1. Okay? What I'm saying is that you have a map that goes from a surface of genus 1 to a surface of genus 1. Now see what happens. So G and G prime are both equal to 1. So this term vanishes. This term is 1, cancels with that one. So it means that B has to be 0. B has to be 0 means that there are no branch points. So in other words, any map from surface of genus 1 to surface of genus 1 is necessarily a default covering map. There are no ramifications.
What about if G equals G prime is greater than 1?
Okay, that could happen. Now, but the case that I want to draw a conclusion is that G is equal to G1. G prime is equal to 1.
Okay.
So, then, so let me put it like this. Then B is equal to 0, i.e. F is always unramified. Provided, of course, it's a non-constant map. If it is constant, then we don't even consider that as part of our discussion. Throw it away. And I gave you an example, by the way, also one of your assignments is the case where you have a map from surface of genus 1 to surface of genus 1. What was that example that I considered? Oh, one of your assignments is actually has to do with this case. Well, how do you construct a surface of genus 1?
Quotient with
Yeah, C over lambda,
lattice.
right? C over lattice. So, and in that case, what was that map that we considered as part of your assignment?
Goes from C over lambda to C over n lambda?
N lambda, yeah, multiply by n. Multiply by n. And that has degree n squared, actually. But that map is not ramified. And we know that but this is a much more general result. So this shows that actually it's impossible to construct any ramified map. So that's So the next case that's important is to consider maps from a general Riemann surface into surface of genus 0, into C hat. And these are actually very important maps. So here is an example of a map that goes from. So next, we are going to construct for a map F from C over lambda to C hat of degree 2. A monomorphic function. So, okay, so first of all, what is lambda? Lambda is equal to Z omega 1 plus, is a lattice plus Z omega 2, omega 1 over omega 2 is not a real number. So this is a lattice, right? So the lattice, of course, you know how to think about the lattice. You have this origin, you have this vector omega 1 in the complex plane, and there's another vector omega 2. And then we just construct this parallelogram and then continue it. So on. So this is a lattice. So these are the points of the lattice. Okay. So this torus, C over lambda is a surface of genus 1, complex surface of genus 1. It's a Riemann surface of genus 1. And what we want to construct, we want to construct a metamorphic function on this one. Okay, to see a metamorphic function, maybe. Yeah. So we want to construct a metamorphic function on this one. So how can we construct a metamorphic function on this on the torus, right? How can we do that? Well, to construct a metamorphic function on the quotient space, you have to construct a metamorphic function on C, which is doubly periodic, because this means doubly periodic. You see, we have this map C, and we have this C over lambda, and you want to define this map, say, I don't know, this F maybe here. So if you do, so the idea is to construct this map. This is projection. You construct this map here that is doubly periodic. And then we know that it gives us a map here, right? So now the question is how you construct doubly periodic function. Okay. So how? Okay, metamorphic. So F now from C to C, which is doubly periodic. So doubly periodic, of course, means the following, right? F of Z plus omega 1 is equal to F of Z, and F of Z plus omega 2, F of Z. right? So this, so just go back to calculus, even high school. So imagine someone asks you the following question: how do you construct a periodic function on the line?
Real line,
Yeah, on the real line, yeah. How do you construct
what period?
period one?
Uh,
So f of x is equal to f of x plus one for all x.
So we define f from 0 to 1, give it a formula, and then we extend the same formula.
That's right. That you can do that, right? But now I insist on having an analytic function. How would you do that?
An R. So first of all, it has to be analytic in the interval from 0 to 1, that's a necessity. And the f of 0 has to be equal to f of 1.
That's right, yeah.
Otherwise, it's not thinking.
Yeah.
And it has to be differentiable at that point too.
Yeah, but we want analytic even.
Does that mean differentiable?
No, analytic means yes, should have power series expansion everywhere.
It's real. Not
Everywhere.
Yeah.
Everywhere.
Okay, give me an example of an analytic function on the line
this period.
with period one. With, oh yeah, sine and cosine functions, right? Okay, but yeah, okay, so that, yeah, so good. Sine and cosine, I want to tell you something that we have been cheated actually to believe that sine and cosine are easy functions and because I ask you a question now. If you can answer this question about sine and cosine, means that okay, so maybe you're not that cheated. So let me ask the question: how do you show that actually sine is periodic if someone tells you that sine function is this? You have the power series expansion of the sine, right? It's sum minus 1 to the n, x to the power 2n plus 1 over 2n plus 1 factorial, and from 0 up to infinity, right? This is sine of it. So now you want to show that sine of x plus 2 pi is equal to sine of x. So how do you do that?
Expansion of sine of x.
So the expansion is here. Yeah. Okay, so you want to put there, and then you get a mess. If you raise this to power.
No. If you do sine of x plus 2 pi is equal to sine x times cos 2 pi plus.
But how do you read it honestly?
Can you use like the Gauss e to the like sine of x equals
You mean Euler's formula?
yeah Euler's one.
Yeah, it's the real part, is imaginary part of e to the ix or something like that. Yeah, but that's a sophisticated idea also that we have been told, and we accepted it without really understanding it. I'm pretty sure. See, the point is constructing periodic functions is a very hard business. It's a very difficult business in general. But there is one idea that always works, and you should have that idea in mind. What is that idea? The idea is if you want to have some condition like this, you average. You just start with any stupid function, which is not periodic, nothing, and then you average over that function, over that group. So you know what I mean? So let me write it. So so the idea of averaging, and this is not the way that, by the way, it's been constructed. This is this formula is the result of almost, I would say, 2,000 years of human activity. I mean, this is not a trivial formula, really. You should not underestimate the importance of this formula, because Greeks, even before Greeks, Babylonians were doing astronomy, and they were using chord tables. If you open, for example, the book of Ptolemy, the famous Greek astronomer, more or less the time of Jesus, 100 years after Jesus, he wrote that book. If you open the book, in the first page or 2 pages, there's a table of chords, which is classic old notation for sines. So he gives the tables, he gives sines of all angles up to 3 degrees, not smaller than 3 degrees, but 3 degrees. So Greeks were quite advanced in computing this sine function, or they called it chord functions, because they were so. But then this formula came much later, but trigonometry, of course, existed. But now the idea of averaging. So what is the idea of averaging? Start with any stupid function f of x. Then you want to make it periodic. So what you do, you average over the group. Okay. So generally replace f to this f. So f of x is equal to sum of x plus n, right? This is a function. Now this is periodic. This has period 1.
How do we know it converge?
Well, we want to choose things to be convergent. That's the thing. So if it is convergent and analytic and everything is okay, which we'll estimate.
Yes.
But the point is that this has period 1.
Can't x go to infinity?
Huh?
Can't that value be infinite?
Sine?
Big F. A big F of x, can't it be infinite?
It can be, but if you choose your f in a good way, you have a chance to make this convergent, and then you're okay.
Oh.
The point is something else. The point is an algebraic idea that if you want to make something periodic, you average over the group. This is called averaging. This is very important idea. Okay, so now we are going to use this idea in the case of not in the case of line, but in the case of lattice. Okay, so that's what we're going to do now. So, and this is what Weirestrass did with Weirestrass P-function. So Weirestrass defined it like this: P of z is equal to 1 over z squared plus sum 1 over z minus lambda squared minus 1 over lambda squared, lambda belonging to lattice, and lambda is different from 0. Okay. This is the Weirestrass P function. I believe this notation is going to do the Weirestrass. Okay, so this is defined for any lattice lambda. Right? And now this function, first of all, so you have to check some analytic points, but these are elementary and you can check it. The first point is that P of Z is defined and analytic in C minus lattice point. You see, if Z is a point on the lattice, obviously you don't have a chance to define it because it's 0 here, right? So you cannot define this over the point. So you delete the lattice points, but away from those lattice points, this infinite sum is convergent and actually uniformly convergent on compact subsets, and it's a nice.
It's a metamorphic function.
Hmm?
It's metamorphic.
Then it is metamorphic exactly because around those lattice points, it has just poles of order 2.
And there are countably many of them.
There are countably many, exactly. And is metamorphic, in fact. On C. And in fact, with poles of order 2, I mean, for example, at 0, you can see that it's just like that.
How do we know, how can we be sure that the pole is low order too? Because it's not a Laurent series or a Power series.
No, but near that point, everything else is holomorphic, even at that point. So the pole is only this part.
What's zero?
What's that?
At zero, what is?
At zero is this one over z squared.
Okay.
But these guys are fine at zero. There's no point. There's no pole at zero. So let me tell you a little bit of a story about Weierstrass. Weirestrass, his father wanted him to become a lawyer or a government administrator. So, but his talent was in mathematics. He loved mathematics, but his father was pushing him to do administrative work, so to become a lawyer, to become high government official, and that. As a result, his life was tormented between doing mathematics, not doing mathematics. He couldn't make a decision. So eventually he quit. He didn't get his degree even. So he was hoping to get PhD, but he didn't even, I'm not sure even he finished his undergraduate degree. So, but he was so talented, they gave him a job as a school teacher. So he became a school teacher in some remote school in Germany in the middle of 19th century. But he kept doing mathematics, and then he came up with this function and this sort of things. And when he published this paper, they invited him to become professor in Berlin. Basically, that's what happened. And so he did this and similar things for complex for holomorphic functions. So he gave a new foundation for the theory of holomorphic functions. So anyhow, so this is this one. So P of Z. But now the difficulty is why this is periodic. Why? Now P of Z plus omega I mean lambda plus omega I is equal to P of Z. Why? Or
What is omega I?
well, I defined it. But these are the two they are the one that define the lattice.
Oh, for both of them, right?
Yeah, I equal to 1 and 2, yeah. So this is the idea of periodic. So this is the question. Why is it periodic? So I mean, if you put here, I mean, lambda to be, for example, I mean, if you just replace Z by Z plus omega I, it's not clear at all that this is going to be periodic or anything like that. So this is a difficult, very difficult, tricky question. But what you can do, you can differentiate this and see what happens. So let's differentiate this.
Is it clear that it's convergent or even uniform uniform?
It's not clear, but it's a part of elementary analysis. So anyone who has done analysis 1 should be able to do this problem. So I won't do that. Okay, so but after class I can explain to you what to do here. So now, so the idea of periodicity, so proof of periodicity. So you differentiate this function. Consider P prime of Z. If you look at P prime of Z, what you get? You get minus 2 over Z cubed plus some minus 2 over Z minus lambda power 3, lambda belonging to big lambda different from 0, right? You get that because that term cancels. And again, this is a holomorphic function. Oh, okay, I mean, meromorphic. Meromorphic. And actually, you can write it now as the form that I wrote as averaging. This is minus 2 sum 1 over Z minus lambda cube, lambda belonging to lambda. And of course, if you look at this, you see that if you translate by any amount in the lattice, you're going to get the same, right? So here this follows that actually P prime of Z plus lambda is equal to P prime of Z for all lambda belonging to the lattice lambda. I mean, this is the idea of averaging here, right? Again, you have to work a little bit to show that this is the holomorphic function, the series is convergent, it's holomorphic, these are elementary. Okay, so now we have this equation. Okay, so what you have now, you have two functions whose derivatives are equal on this connected open subset of the plane, which means that the difference is a constant, right? So here it shows that P of Z plus lambda must be equal to P of Z plus some constant C for all lambda belonging to lambda. So now I have to prove that C is equal to 0, right? So the question is why C is equal to 0. Yeah. So first of all, we notice that this function P is an even function. So in the sense that P of negative Z is equal to P of Z. You see that? P of negative Z is equal to P of Z.
I don't see it.
Huh?
I don't see it.
You don't see that? Okay, so yeah, let's write the thing. Yeah. So what was P of Z? It was 1 over Z squared plus sum, right?
Oh, right, okay, yeah. Yeah.
1 over Z minus lambda squared minus 1 over lambda squared. Lambda belonging to lambda, lambda is different from 0, right?
Mhm.
Now, if you change Z to minus Z, you're going to get the same value. Now, the only thing is why here you, what's that? You can do negative, but negative lambda and lambda are the same things on the, this is a kind of group property actually, exactly. So that's okay, excellent. So now, so we have this equation, P of Z is equal to P of Z plus lambda plus C. Now, if I just choose, so okay, so let's choose like omega 1, for example. Here is omega 1, and here is omega 2, right? So if I choose for Z to be maybe negative omega 1 squared, also omega 1 over 2, then you conclude that P of negative omega 1 over 2 is equal to E of omega 1 over 2 plus C. But this is an even function, these two values are the same, so C is equal to 0. C is equal to. So this function, in fact, is doubly periodic function. I mean, you can change omega 1 to omega 2 and then choose somewhere in the middle, right? Okay. So that's very nice because now what we have is that we can consider this function actually on the torus because it's doubly periodic, right? So P C or lambda C, so it's a meromorphic function.
Doesn't it project?
Sorry?
Doesn't it project it?
No, okay, so what I mean is the following. You see, we have this picture. So we have this picture, C over the projection map, right? C to C over lambda, right?
Yeah.
And what I have is originally we considered this function here, right? To C. And what I mean is
Suppose it is a projection now. No,
Yeah, you can say projection, but I cannot maybe say lifted, but yeah. You see, what this function is that P of, because this is an equivalence class, right? And because of double periodicity is okay. Anyhow, so either way, we get a function, which is, so this is what we want. So, where are the poles of this function now? Here, on the torus. Where are the poles of this P as a function on the torus?
that's just one pole.
It's just one pole, exactly, because all those 4 points, lattice points, all that they come together, form 1 point, right, in the quotient. Exactly. It has only one pole here, and this pole is a pole of order 2, because it corresponds to 0 or to lattice points, right? So just one pole of order 2. So what happens, this map P, Weirestrass P-function, gives us a degree 2 map from the this torus elliptic curve into P1. So what I'm saying is that P is a degree 2 map. So it has one pole of order 2. So what about its zeros now? What can you say about the zeros?
Aren't they the same number? Well,
Number of poles is equal, counting multiplicities is equal to number of zeros. Counting multiplicities. So the question is, so the total number of zeros has to be 2. So either it has 2 distinct zeros or 1 zero of order 2. Which one is? It's not easy to guess, actually. I don't know the answer myself. I have to think. I just asked the question for you to tease you to think about it. I don't know the answer. It's a nice thing. It's known since Weirestrass know that. So, but it's good to think about it. Yeah. So, and then optimal multiplicity. 2 zeros. Counting multiplicities. So this is a cool, nice, very important map from elliptic curve for now into the that goes into Riemann sphere. But then we are going now to also involve P prime in the next lecture. I'll use P prime to define a map which is actually goes into the affine model for this elliptic curve, and then it's called Weirestrass parameterization of the elliptic curve. So. Okay, any questions, or so let me now stop. But do ask questions, please. Yeah.